Good morning and a warm welcome, everybody, to today's Web Seminar Wednesday. Today, we have Olin as guests and two motivated speakers, Lars Friedrichs and Martino Lamaccia. And the title of today's presentation is Rebar Pullwinding. It's not pultrusion. So I really look forward to their presentation. And with that, gentlemen, I leave the stage to you, and I look forward to your presentation.
Perfect. Thank you very much, Bastian. And I hope you hear me okay. Perfect. Okay. So again, welcome everyone to our webinar. My name is Martino Lamacchia. I'm Global Product and Marketing Manager for Composites at Olin Epoxy. Before, deep diving into our process review today, so pullwinding, it's not pultrusion. Let me spend 10 minutes for a very quick introduction. I will start with a quick introduction about Olin. So Olin is an American chemical company founded in 1892. Our 2022 revenue was around 9.4 billion, and we are 8,000 people. And the company is listed on the stock exchange. Now, while I don't want to bore you with the full history of the company, let me just mention 3 milestones that I think are relevant for our discussion today. So, as I said, 1892, the year when the company has been founded. Actually, 2 companies were founded in 1892, Olin Industries, a manufacturer of ammunition, and Mathewson Chemical Corporation, the first company to make chlorine in the US out of the chlor-alkali process. So chlorine is really in the soul of this company since many, many years. Then I skip some milestones. In the 50s, these 2 companies merged together, originating a group active on chemistry and ammunition. And Olin is still today that kind of company. And then I'm skipping to 2015. Very significant milestone for our discussion today. Olin acquired from the Dow Chemical Company the global epoxy business and the US chlor-alkali business and the global chlorinated organics business. So transformative acquisition for Olin that actually, as we can see in the next slide, that transformed Olin in the #1 global chlor-alkali producer, and again, importantly for our talks today, the #1 global supplier of epoxy materials, inheriting this position from the Dow Chemical Company and bringing it to the next level. So today, Olin is divided into 3 businesses. Olin chlor-alkali products and vinyls, Olin epoxy, the business Lars and I are part of, and Winchester, which is our ammunition business. So let's now focus on Olin epoxy. What is Olin epoxy doing? Well, in 10 seconds, we are leveraging epoxy properties like corrosion protection, lightweight strength, electrical insulation, chemical resistance, to approach those markets where these properties are valuable, like coatings, electronics, civil engineering, and importantly for our talk, composites. Now, if you want to remember one thing about epoxy, about Olin epoxy, I would really try to remember our model, right? Our deeply back integrated model. But before going into that, I don't know how familiar each one of you is with epoxy, but hey, from a very high level, you could say to make epoxy, you need 2 things, epichlorohydrin and bisphenol A. Now, most epoxy producers run a non-back integrated model like the one you see here on this slide, right? So they source epichlorohydrin somewhere, bisphenol A somewhere else, and they make their epoxy resins. Now, while this model could have some advantages like lean assets, for example, we think it does show some question marks. The first one is reliability of supply, right? Any one of you who has sourced epoxy resins in 2021, beginning 2022, knows that shortages in epichlorohydrin can cause severe headaches to non-integrated epoxy producers. The second question marks that comes to our mind is scalability, right? Hey, epoxy resins are linked with many high growth mega trends that are shaping our times, from wind energy to advanced electronics to composites. So the world will require growing amounts of epoxy resins in the next years. A non-integrated model means that, yeah, you depend on someone else, right, to build up that additional capacity that the world will need. And the third question mark we see on a non-back integrated model is sustainability, right? If you need to move around the world ships and ships of epichlorohydrin, bisphenol A to make your epoxies, the carbon footprint of your epoxies is not going to be very attractive. Now, Olin model is completely different, as we can see in the slide here. Olin is deeply back integrated on those molecules that we think are strategic for our reliability of supply, for our scalability, for our sustainability. Look, for example, at epichlorohydrin. We start from digging our own salt mines. We make with that salt chlorine out of electrolysis. From there, we make allyl chloride, we make our epichlorohydrin, and then our liquid epoxy resins, right? So a deeply back integrated model that gives us the reliability of supply, scalability, and sustainability that we need to make our products. And hey, this model is applied to a very wide portfolio of epoxy products. Some of these products are actually part of our composites portfolio, and that's where we come to our topic. Now, in our composites portfolio, as you see here, we have systems for pultrusion, filament winding, infusion, hand layup, HPRTM, pre-preg. And I think the composite portfolio is one of the portfolios where our, again, deep back integration is very valuable, right? If you look at these applications, at these technologies, they are linked to high growth applications, right? Pultrusion, as we will discuss today, composite rebars, but also applications in wind energy. Filament winding goes into hydrogen mobility. HPRTM goes into e-mobility. So high growth applications where we think that our back integrated model is valuable to supply or to offer the supply reliability and scalability that these high growth applications will need. Good. Now, in composites, what we see is that it's really not enough to sell a product, right? Process knowledge, process understanding is what we need to share with our customers to actually make them successful. And this is a bit what we're going to do today. So in the next slide, we are introducing the topic of today. We will speak about pultrusion and pullwinding processes with focus clearly on pullwinding, explaining the specifics about pullwinding and why we think pullwinding is definitely not pultrusion. We will use as reference application for our review today composite rebar, which is made in pullwinding, right? And we will demonstrate that, hey, to make a quality composite rebar in high productivity is really not enough just to pick a standard pultrusion system, right? But we need something specific, and we will talk about our lightstone epoxy systems for pullwinding of composite rebars. But before going straight into the process review, let me maybe answer one question, which is, hey, why epoxy, right? Why Olin, the leading epoxy producer globally, is talking today about rebars and pultrusion? Well, we think epoxy in rebar pullwinding has three main pillars in its value proposition: mechanical performance, high chemical resistance, and EH&S profile. So under a mechanical performance point of view, I mean, we know that among the available epoxy matrix, among the available composite matrices, epoxy is at the top end of mechanical performance, right? With specifics to the composite rebar, this enables to meet and exceed all the actual regulations like ASTM D7957, 8505, or F.932. But that's not all, right? Because yeah, epoxy not only enables to meet those specs, but it also enables to retain those specs when actually the rebar is subject to the attack of specific chemical agents. And that's what we are showing in the next two slides. I will not go into the details, but what we are showing is that not only are we matching the requirements of the specs, but we are also retaining those specs when the rebars are subject to the specific tests of these norms, like alkaline resistance tests and so on. And this does not only happen for glass fiber rebars, but it happens also with basalt fiber rebars. So chemical resistance is definitely an important pillar of epoxy proposition into rebars. And then last but not least, we come to sustainability, right? I mean, epoxy is a solvent-free, a fully solvent-free matrix, which means it's not flammable, which means it's friendly for the workers, right? And when it comes to, installing production capacity, when it comes to expanding production capacity, it means that this capacity happens at, or capacity increase happens at lower cost versus other matrices that use solvents, right? Flammable solvents. So with epoxy, you don't need, you need simpler exhaust systems. You don't need an EX protected area. You don't need cold storage. So all that leads to a kind of lower CapEx when installing or expanding capacity. So this was the answer to why epoxy for Pullwinding rebar. And now it's really time to go deep into this process review, pultrusion versus Pullwinding. And for that, let me turn it over to my colleague, Lars Friedrich.
Thanks, Martino. Yeah, short introduction also from my side, also welcome. Yeah, Lars Friedrich, T&D manager at Olin, based in Stade, and I'm the technical lead for all, let's say, high productivity processes like pultrusion, Pullwinding, but also other topics as mentioned, HPRTM, LCM, and so on. So really the essential of this for us, or important part, is to point it out, what are the differences between pultrusion and Pullwinding, and what are really the effect on the material selection is. So first, I really would start with I think the key message. So what is really the main difference between pultrusion and Pullwinding? So at the end, it's really the cure scenario, how you cure your resin. So in pultrusion, where you have a well-defined shape, you have a closed mold where you gelate and cure the resin. So which means you created in this closed mold a kind of friction, which leads to higher pulling forces. And there you have specific requirements on the resin, which is linked to this. I will come to this in a minute. In Pullwinding, you have I would say, completely different scenario. You just impregnate it, form it, and then you have a wet, let's call it profile, which consolidated by winding, and then you pull it through an post-curing oven. So it's a freestanding cure. So it's not in contact with any dye doing the cure. So all the challenges which are related to pultrusion are not given. So that means that for these two processes, the requirements on the resins are really different. You can use both of them in the other process, but it will have a negative impact on productivity, quality, or whatever. So just as a scenario, I will not go too deep because I think pultrusion, it's well known. So you pull your fiber through an impregnation unit, often a bath. You have a heated dye where you cure it, and then you can wind it or cut the parts. In Pullwinding, you have the same up to the impregnation bath. Then you have a kind of preforming unit where you just form your profile. Afterwards, you have a winding station to consolidate this profile, and you have a post-curing oven. So really, as described before, the cure scenario are quite different. So what it means it now really for the resins themselves. So if you're looking and compare the protrusion and pull winding, so processability. So for the protrusion, I would say it's a, yeah, let's call it more sensitive process, because you have really to find a good balance between processability, line speed, so phase quality, and so on. And as you cure it in the die, you need a really accurate method to manage the pulling forces, which is also related then to part quality or to phase quality. In the pull winding, as you have this freestanding cure, these issues which are related to this closed die are not existing. So that means that from processability point of view, pull winding, it's much more robust. It has a bigger process window. It's not so sensitive for distortion and so on. Internal release agent, so in protrusion, it's required. Otherwise, you will have a significant issue with your pulling forces and or the phase quality. In pull winding, as you have not really a closed mold, it's not required. The key requirement on the process control, on protrusion, as mentioned, you have to find a good spot between positioning of the gelation point in the die to minimize the pulling forces and optimize the surface quality. But on the other hand, you will also optimize your outputs, so your at the end line speed. So there you need really a kind of well defined way to do this. In pull winding, I will go deeper in this in a minute, but at the end, it's really that you need an adapted viscosity behavior to manage the resin flow in your process at different stages. I will come to this. So what it means really for the resins themselves. So at the end, for protrusion, you need really a kind of adapted Q kinetics to control the reaction, to be able to establish a process robust or a robust process. There are different ways to do this. I think we give different webinars on this topic. I will not go in too deep in this today. On the pull winding side, there for sure you need also an adapted reactivity, which is a little bit different to the protrusion one, to control the resin flow in your process. And for sure, higher reactivity to maximize your output, so you have a little bit more freedom in the pull winding process. And this can be really used to increase the line speed. So for this reason, we as Olin have developed two different product lines for protrusion or pull winding. Maybe not, or different optimized grades. Let's phrase it in these words for these two processes. I will come later to this. But what I would like to do first, it's really go through the pull winding process and define the critical process steps from resin point of view. So what are really the steps in the process which limitates line speed, what should be focused on to create a high quality rebar or profile. So the most important step, it's really the impregnation. So key criteria here, it's for sure we have to ensure that there is a sufficient and good impregnation at targeted line speed. So that means for high productive processes like the rebar production, we're more discussing 5, 10, maybe faster. So that means that here are the requirements on the impregnation are different than in comparison to protrusion, where we more discussing a range up to 1 meter per minute and maybe now going also slightly higher, but it's a completely different range. So, and here the key criteria from resin point of view, it's a start viscosity of the resin themselves, and for sure the pot life if you are using an impregnation technology like an impregnation bath. But what I also would mention from my point of view is the impregnation also the limiting factor for the line speed of the production. So, and this is mainly, I often say we need a high reactive system to run this the line fast. Yes. So it's for us not really a problem to create a high reactive resin system. So we can make it as fast as you want. The problem is really then the processability. And in the Q&A setup of a typical Pullwinding line, it's an impregnation unit, it's a bath. So that means you have pot life requirements. And this is really a limiting factor for the resin reactivity of epoxy systems. And if you go to high line speeds, you need also to make sure that you have a good impregnation. And there is for sure the resin important, viscosity, wetting behavior, and so on. But it's also the way how you bring the resin to the fiber. Simple bars, how looks your bars. I will come to this in a minute. But it's not only the resin which define what kind of line speed can be achieved. It's really the combination with the impregnation. So and this is something which can be optimized. We have a lot of ideas around. I will come to this later. But this is something which should be in mind, that if we discuss in productivity, it's as usual the combination material and process which have to be optimized. And the key is here for this process really the impregnation unit. So what are the critical parameters for the impregnation? So as mentioned, it's the impregnation technologies themselves. It's a simple bath. For other technical processes, you transfer rollers or whatever it's are used. It makes probably not sense for all applications, but the technologies themselves and the resulting limitation are really some of the critical parameter for the impregnation. Fiber type, I think it's also clear. If you try to impregnate a carbon fiber, it's a different story than a glass, but also in between different glass types, for example. The sizing has a big impact, the quantity of the sizing. So it directly impacts the impregnability. And this has to be considered when you design your process and your part. For sure, the resin, no doubts. So retargeting for Pullwinding viscosities below 1000 millipascal second at room temperature for bath impregnation. The dwell time in the resin, so which is a function of the line speed and the immersion length in the bath in this case. It's clear if it had more time, then you have a better impregnation usually. The fiber tension and guiding, it's often not considered. So if you have, for example, high tension toe, it also closes the toe, makes impregnation more difficult. But also the fiber guiding of this toes has to be optimized so that it has a good access. So if you bundle a few rovings and guide it through a bath, so the inner rovings don't have access to the resin, so the wetting will be bad. So that means if you have a more homogeneous distribution, could be helpful. Spreading, for sure, it's also important. So to flatten it, that there's better access. So everything which is related to fiber guiding, tensioning, directly impact also impregnation capability. Some recommendation in terms of optimization of the impregnation. So for sure, as mentioned, it's really the design unit themselves has to be optimized. I think it depends really on different parameter, how it can be looked like, how sensitive is your fiber. Some fibers are break at every deflection, others are really robust. The pot life of the resin, is this an issue? The viscosity, and for sure also kind of pulling forces, which is in Pullwinding usually not a problem, but you can create also pulling forces in the impregnation unit, which maybe lead, if it's too extreme, to issues. Fiber preheating, it's also to be recommended. First, to softening, especially with glass, the sizing. It helps to open the glass rovings. Also, if it's preheated, the resin, let's call it froze not on a cold fiber. So that means if it's go into the fiber bundle, the wetting and impregnation is better. Otherwise, you have a local viscosity increase and you created a kind of micro porosity in these areas. So it's really helpful if the fiber is preheated. And for sure, if you have a fiber preheating and then you have a bath behind, you also bring energy in your bath, which is usually not a problem, but if it's too extreme, it can have a significant impact on the pot life, depending a little bit on the setup and systems and so on. But this is something to be considered, which is for impregnation normally to manage, and can be also helpful to control the resin flow in later stage. I will come to this. So one other option for sure would be to operate if you go with a heated impregnation bath. So just by this, you can reduce the resin viscosity, and this will be simplify the impregnation. And you can also minimize the resin volumes in the bath or in the impregnation unit. This would be really open the door to use more reactive resins. And then for sure, you have also higher line speed potential. As mentioned, key requirements from impregnation point of view on the resin is a long pot life, which is a limitation for our reactivity. Low start viscosity, good wetting performance. So lower viscosity help for sure. And it should be solvent free, just from EH&S point of view, to minimize the emissions, as you often operate in an open bath. So the next critical step would be really then the winding unit and preforming. So here, usually, I think it's not the most critical step, but here often you need a kind of sufficient resin flow to impregnate the winded toes or plies. So that means at this stage, you need to understand and control the viscosity of the resin at these stages. The preforming unit. So the function of the preforming unit, it's usually bring the roving in the shape of the part, define the ratio between resin and fiber, and bring it to the winding station. So that means that for sure the design criteria then for the preformer are the part design. Then you have to define what kind of accessory resin it's needed to impregnate later the winded toes or plies. But there's also a potential need to extend a little bit the functionality of the preformer. So if you have, let's say, a bit more challenging fiber, which needs or higher viscosity systems, you need to force the resin more in the fiber. So that means that you have to extend or integrate a kind of impregnation step. So for example, just a few deflection bars on the way from the roving from the bath to the forming station to further improve the impregnation in the toes. Really to be validated what is required, and depends for sure on fiber and resin. And in this step also pulling forces are created. So you have to pull the fiber through something. If you have this deflection bars, you have additional forces. So that means that it's some forces are created, but also this can be also not negative. To some extent, pulling forces are also good to improve the performance of your profile. So you have a better alignment. It's also, if you have later the winding step, you have a kind of higher resistance in terms of deformation of your fiber alignment. So that means that by controlling the pulling forces and increasing it maybe to some extent, you can also improve a little bit the performance of your final profile. So for sure to be validated, but it means that in some cases, it also makes sense to initiate or add an element to create really pulling forces and to control this. But this really has to be validated on a profile and the resulting performance. So in terms of requirements, so the critical part is here, if you wind it and, for example, the viscosity it's too low, then there's a risk that you squeeze it out, that it's a kind of deformation of your profile. So that means that here the resin viscosity at the winding station it's quite interesting. It's a function of the start viscosity for sure, but also the thermal history. So that means, have you preheat the bath? Is there some infrared heater for the fiber spreading? Have you a heating system in front of the preforming unit? So it means, is there any temperature or energy which pre-aged the resin before the winding station? Often, in most cases, not too much, so that is not a big effect, but it can also be used to let's say, overcome issues if this is something which is recognized in the process development. The resin flow, for sure, it's also defined by the amount of the excess resin. So if you have more resin on your profile and you have a kind of force on it, it's squeezed out, especially if the viscosity is too low. And the winding tension themselves has to be also optimized to ensure a good consolidation of your part. But on the other hand, don't squeeze out the resin and not really deform the directed fibers. So the next critical part is the oven entry. Here you need to control the resin flow to avoid really the resin dripping. And this is, I would say, the critical, or the most question which I see, it's really related to this point. And it's really related to the resin in the way that it's the viscosity at the oven entry and the reactivity, because there you start really the gelation and the reaction and the viscosity build up. So what it means, for sure, in everything before the oven, you have maybe some temperature which has an impact on the viscosity of your resin, kind of aging. But often it's a quite simple setup, just pulling it through, no real aging. But if you then go to the oven, here you have, for example, a viscosity of 600 millipascal second, but then you heat up here the profile and the resin, so which means the viscosity drops to some extent. And then the reaction kicks in and then viscosity is built up. But you created here a viscosity minimum at the oven entry. And the effect of this is you have a kind of created often kind of resin drops on your profile. In worst case, this resin flow in your oven, contaminated, and so on. So it's really a, I would say, typical challenge in the process, which has to be managed. So two options from our point of view, from resin point of view. So as mentioned, first would be really to age resin in front of the oven by some heat treatment on the way. So just to build up some viscosity, that is minimum viscosity will be not too low. Or you really have a kind of specific cure profile in your oven, so that the first zone, it's not at whatever 200 C that you maybe start with 120, 140, just that the viscosity goes down not too much, and then the viscosity is built up. So this is a way to minimize this effect or avoid it completely. So this 12 step, also this has to be looked depending on line speed and so on. But this is something which is quite effective to overcome this. So the last critical step is the cure themselves. So from process robustness or quality point of view, it's here really the cure speed and the degree of cure. So how well cured is your part. So this is really the criteria here. And this is for sure related to the reactivity of your system. And this is also, I would say, the reason why the impregnation is a limiting factor. So in the front, you need less reactivity to ensure a good and long pot life. On the end of your line, you would like to have a high reactivity to speed up or to shorten your oven, whatever is your preference. But there's a little bit a fight between these two requirements. So as mentioned, it's a freestanding gelation and cure in the oven. So it's regarding friction and interaction between a die, it doesn't make, it's not a problem. So it's really the function of how you achieve the degree of cure at the oven exit. So and this degree of cure is a function of the thermal history of the resin. So mainly for sure in the oven, but also everything which is in front of it. The temperature profile in the oven. Here to be considered that the temperature settings of a post-curing oven are not the temperature which are effective on the part, but I think it's everybody who was operating this kind of equipment is aware of this. So, but I think it's quite important to understand what are really the temperatures on the part and how this correlate to the set points. The line speed, so this defines the time in the oven. As mentioned, system reactivity. Higher reactive system for sure have higher line speed potential. And critical for sure is also the dimension, especially in the rebar, if you go to thick ones with glass. You have this the feature of a glass fiber that the heat conductivity of glass is not so good. So that means it takes some time to heat the center of your profile. And this is something which it's hard to overcome. So you need some more time. So it will be slowed down the process. And this is something really to consider. So also here, what could be helpful to increase your productivity? So for sure, it's a function of the selected resin system. So it means how the impregnation looks like, how fast you can run the system at a good impregnation, what is the reactivity, the impregnation unit to enable the impregnation, and the thermal history of the resin in the production line. So now really to maximize this, first important point, it's really to optimize your impregnation unit. In best case, really to enable the use of more reactive resin systems. So you, for example, in a simple way, create a bath which you don't require the pot life of several hours. Maybe 1 hour is sufficient. Then you for sure can accelerate the system much more. Also a way to improve the impregnation at high line speeds by changing the tensioning, guiding of fibers or whatever. Fiber preheating, it's quite efficient in terms of impregnation. Pre-age the system before the oven. As mentioned, it's helpful to control the resin flow at the oven entry. So which also means if this is not required to put high effort in the avoiding this resin dropping, you can be more aggressive with the temperature profile right from the beginning in the oven. So that means you can run faster. And for sure, the simplest one would be just to extend your oven length. So I will not bore you too much with our portfolio, only 2 slides. So first, as mentioned, we have two grades, or let's say a group of products. So first for pull winding. So here we really targeting line speed above 5 meters per minute, good impregnation at high line speed, higher reactivity. So characteristic here more from viscosity point of view on the lower side, and it should be more reactive. For protrusion, there we have really targeting more the line speed around 1 meter per minute. Good impregnation at this line speed. Here we have a little bit more freedom. Here, more the key, it's a high process robustness. As mentioned, the protrusion system is more sensitive due to the fact that it's cured in the closed die. Here we put a lot of effort. I will not explain, but this is something which makes a big difference in comparison to pull winding. So that means that we here have a resin characteristic, an adaptive cure kinetic, so to enable the control, and let's say an improved sliding behavior in a closed mold. At the end, we have a portfolio. I will not go in detail through this. I would only point it out two things. First, if you compare, we have two standard grades, one for pull winding, a hardener 3101H, and for protrusion, the 3102H. And if you compare the two systems, you see a significant difference in the viscosity. So protrusion, it's higher. So as mentioned, we are targeting not high line speeds, so we can accept that the viscosity is higher. The impregnation will be still at this line speed able with this kind of viscosity. In pull winding, this can reduce it just to open the line speed potential, and it's also slightly more reactive. It's not visible here. To mention, both system can be also further accelerate. So if you have really a process where you can handle shorter pot life and so on, we have also the option to further accelerate the system and increase productivity. If any question to this will coming up, just let me know. But at the end, we really pointed out that we would highly recommend to look what is your requirement and then select the adapted system for this. For sure, you can using also protrusion systems in pull winding. It will work, no problem. But if you're looking in a way to maximize your output and productivity with an adapted system, you are on the better side. So my summary, first, it's protrusion and pull winding are not the same. So as I try to explain what are the reasons for it, to optimize for your process and the productivity, you should be carefully look in an adapted system and maybe also find a good way to adapt and coordinate the resin characteristic in your process setting. From my point of view, also the impregnation is the main limiting factor, as explained, due to the impregnations themselves and the requirement on pot life. And we have system in our light stone portfolio, as mentioned, which shows an excellent performance, which also qualified against different standards, especially in the rebar specifications. Yeah, so this is really my part. Thank you for your attention. If any question coming up, so I'm the technical contact, so just feel free to go in touch with me. And then I would say, Bastian, up for questions, or?
Yes, thank you, gentlemen, for this great and very interesting web seminar.